Okay, Sig Figs Volume 2. Oh, come on, pen, just write. Sig Figs Volume 2. So yesterday, we looked at some fairly straightforward examples, and we said, well, like, what would happen if we were to add up two different chunks of gold, right? And what values we could actually say when we were finished adding them up without line, right? And the whole concept was that if these were measured on different scales that had different precisions, the math would not really, give us a correct value. And just to quickly remind, in case people weren't here, what we said is if we have two expensive metals or chemicals or whatever, and we have two different scales, one that goes to this and one that goes to, say, that, this scale might cost $7,000 and this scale might cost like a few $100s, but we want to know the total mass of A plus B, okay? Well, let's say we got 4.2 grams off this scale and, 16.6523 grams off this scale. This one has a tolerance plus or minus 0.1, and this one has a tolerance of 0.0001, okay? If we just straight added them, you'd get this, 16.6523 grams plus 4.2. For math class, you'd bring down the 3, the 2, the 5, the 8, and the 20, and you would just leave it like that. That's what your calculator would give you, okay? We said there's a problem with this. The problem is our other scale can't tell us these values. There's very little chance they're actually 3 zeros. So to write this and say, this is how many grams of gold I have is incorrect. You're saying you have more precision than you could possibly have. So we're going to access significant figures rules to figure out how to deal with this. And the significant figures rule that we're going to talk about is the one for adding and subtracting, which just says you have to round to the value with the lowest number of decimal places. This only has one decimal place, so we're going to round this number to this value. We can only report it with any confidence as 20.9 grams, okay? And then we said we would bring down the largest tolerance, okay? So there we go. That's how we would write that. Now, we don't have to focus too much on tolerances, okay? We'll just mention that they exist. So we'll talk about them more next year. But that's how we would deal with that, and that's why we would round off this number, okay? So that's adding and subtracting. I think it makes pretty good sense, but it gets a little bit more complicated if we need to deal with multiplying and dividing, okay? Okay, so we just did a little side project where we try to find the area of an object, and every group came up with a slightly different value. But one thing that was sort of universal was groups reported too many digits, all right? So too many digits. And remember, when we're measuring, those digits that come after decimals especially indicate precision, right? So we're saying our precision was too high based on the measuring tools that we had. And let's look at why that is. Okay. So we want to find the area of a shape, okay? And we maybe measure this to be, with a millimeter ruler, 452.72 centimeters, right? Remembering that that's an estimated digit, plus or minus 0.05. And then we measure this side, and we'll get it's like, I don't know, 248.63, plus or minus 0.05. I say find the area of this. Okay? So you punch that into your calculator. These represent centimeters, right? And you get a number that looks like this. 112,559.7736. Okay? So in other words, my calculator will tell me that I know this to the nearest tenths, hundredths, thousandths, 10,000ths of a square centimeter. Okay? See as how the best I could do is an estimated hundredth of a centimeter it does not make sense that it would be ever possible to report it to this amount of precision based on the input measurements, right? There's just too many digits here that are not, they're unknown, right? You know, really, we don't actually even know this digit is actually true because we had to estimate it from our millimeter ruler. So how do I deal with this? Well, there's a very simple rule. When multiplying and dividing, okay, all you do is you round your final answer to the value, the input value with the lowest number of significant digits, okay? So there's 1, 2, 3, 4, 5 here, and there's 5 here. These are significant digits to 5. This can go to 5. So we start at the high end and we say 1, 2, 3, 4, 5. This is the best that we can do. So we round to that value and we write the number like this. 1, 1, 2, 5. Well, I look at the next digit to do my rounding. It's a 9, 6, 0. 1, 2, 3, 4, 5 significant digits, and that is the best I can do. I'm not going to propagate through the tolerances or the uncertainties right now. We're going to leave it at that. That's the best we can do, okay, to take into account the fact that we have estimated digits, okay, and we only have a certain number of significant digits going into our values. This is saying we know it way too precisely. If we wrote this in a scientific journal and said this was the area, people would like crush us, okay? This is the absolute best that we can do, okay? 5 significant digits, and we just go ahead and round. So for adding, we just go with the lowest number of decimal places. For multiplying and dividing, we simply round to the number of significant digits equal to the one with the lowest input number. Well, these both have 5. If one had 4, we can only show 4 here, and we'd have to round to this digit. But since we both have 5, we can go to 5. Okay, so the next question is, what values are considered significant to begin with? So here they are. 1, any non-zero digit is significant. Okay. Trailing zeros are not significant. So this is not a significant digit. Not sig. None. Okay, trailing zeros are not significant. There's kind of a caveat on that, though, and we'll talk about that in a second. Okay, so for numbers less than 1. Okay, so for numbers less than 1, leading zeros are not significant. Okay, so we'll pause there and take a look at a few examples. Okay, so 1, 2, 3, 4, 5 sig figs there. That has 1 sig fig. This has 2 sig figs. Okay. Zeros between sig figs are significant. So that has 1, 2, 3, 4 sig figs. 5 zeros after sig figs on numbers less than 1 are significant. What do we mean by that? So let's say we had 0.0670. These zeros are placeholders. They're not significant. These are non-zero values. They are significant. If we add this 0 on here, we're telling the people that the measurement was to, you know, tens, hundreds, thousands, 10,000s, we must have taken this measurement and it worked out to be 0, or else we wouldn't write it. So this has 3 sig figs. Okay, sometimes we run into a problem. Let's say we've measured a value and it comes out to something like and let's say that we know these are significant values. We actually measured this distance, and these are significant digits. How do we indicate to the person reading that this actually has 4 sigs? How do we do that? There's a few ways. Okay, one way is by the tolerance. Okay, the tolerance could indicate to the person, we're writing the tolerance in there, the tolerance would indicate, like if we said plus or minus 0.0, oh, sorry, plus or minus 0. Nope. Plus or minus 1 centimeter. There we go. Let's say. Okay. Now we know that that 0 was significant. Okay. So it's a measurement of 0. So that would indicate that. But if we're not dealing with tolerances, or we want to indicate to that someone, the way we can do this is using scientific notation. Because any digit written in scientific notation is considered to be significant. So we could say 4.200 times 10 to the 3. And that would indicate to the person, if we bothered to write these zeros in, that those zeros are meaningful. Those are significant zeros, and we want them to be included in our measurement. Okay, so just a little recap. When following significant digit rules, really what they are rounding rules or rounding guidelines, so that when you report a value, especially if you've had to add or subtract numbers or multiply and divide them, that you are not reporting digits to indicate a higher precision than your measurement tools originally allowed. Okay, scientists follow these rules just to help them quickly, round off and not over indicate the amount of precision that they had. Okay, so they're rounding rules, right? When you add or subtract, round to value with lowest digits after the decimal place. Okay, so that's pretty straightforward. And when you're multiplying and dividing, okay, round so that your answer has an equal number of sig digits or sig figs to the input value with the lowest number of sig figs. I'll just do 2 more quick examples here. Okay, so example. Find the volume of the following shape. Let's say you're given a shape that looks like this. Cube-like, quite a cube, but cube-like. Okay, and let's say you measured this side to be 472.60. This one to be 4.002 times 10 to the 2. Okay, and this side to be 37.8. I'll leave it at 37.8. Okay, and we'll say all these are centimeter values, and you want to find the volume. So the first thing to note is how many sig figs in each of these values. Well, this one has 1, 2, 3, 4, 5 sig figs, 1, 2, 3, 4 sig figs, and 3 sig figs. Okay, 3 significant digits. So these might have all been measured with different measurement tools or using different techniques. We're not really sure. We just know that we're given these values. Okay, so let's use them to find the volume. All right, so my calculator gives me a number that looks like this. Okay, 8, 0.56 centimeters cubed. Now this is showing way too much precision, right? We only had a maximum of 3 sig figs here. So we just have to take this number and get to round it off to 3 sig figs. 1, 2, 3. Okay? We report it like this. 7, 1. Look at the 9. The 9 rounds that up. The rest of the digits set off to 0. Okay, we don't show any decimals because if we did show decimals, okay, that would indicate that those were significant values. Okay, so that's a number after a non-zero value and after a decimal place. If I start writing zeros here, these now all of a sudden mean something, right? Because if they weren't there, right, if they didn't mean something, I wouldn't bother to write them in. So, you know, if this is a mathematical value, we're going to start indicating more precision than we had if we start adding zeros over there. So we don't add anything after the decimal place. Those would be significant digits if we had to, but we don't. And this would be the correct way to show the volume of this shape obeying significant figure rules. So round to 3. There's one other little side note here with how you deal with rounding. So if we always take 5, we always round up based on 5, what you end up with is a bit of a bias towards, you know, rounding up. So this is not something that's like super important, but I'm going to mention it anyway. So I'm going to draw a bunch of values, and we're going to say these all have to go to 2 sig figs. Okay? How do I deal with them? And it's easiest to just use an example here. So just give me 1 second to write them down. Okay. All right. So for the first one, it's pretty straightforward. There's not a 5 there, so that just becomes 6.4. Remember, we need 2 sig figs in all these values. 6.46. Okay. Well, that's going to round it up. No question there. 6.5. Okay. If it's 6.451 though, you look at this digit, okay, the next digit over, and we say if the 5 is followed by an odd digit, okay, then you maintain the digits that you have. So just to get that straight, okay, so the digit we need to look at for rounding is a 5, right? If that 5 is followed by another digit, we will always round up. So that becomes 6.5, right? So there's a 5 followed by a digit, we round up. Okay. All right, this is followed by a 9, so it just rounds up. No problem there. Okay. Now the digit that we have here is a 5 that we're looking at. So we want to know what happens here, but there's no digit after it. Well, the rule is if we have an odd digit here, 5 is odd, we're going to round that up. So it actually becomes 6.6. Okay, if we have a 5 but with nothing after it, okay, this actually maintains. So the rule we're following here is if you're looking and your rounding digit is a 5 with nothing after it, you have to do this. Okay, so if it's an odd digit, odds round up. Okay, if it's an even digit like 4, you maintain the digit. And the only time you're ever going to run into that is if the digit that you're using to do the rounding by is followed by nothing. If it's followed by any number, then just round up like you would with other 5s. And I think that the key thing here to understand is that if you didn't do that, if you always just rounded 5s up, over time, over many measurements, you bias yourself towards rounding up, okay? This is really the only time anything weird comes out of this, and it's such a rare occurrence that often we just kind of overlook it. But it does exist, and it's kind of like a sort of another rule of thumb in dealing with how to round this stuff. And that's the end of that.